the atoms, they're in a crystal, so they're periodically arrayed, and so to analyze the quantum mechanics, you can do the quantum mechanics of the conducting electrons, the electrons that move with these delta wells all over the place in a periodic array. So we'll be able to analyze that using this difference in gradient technique. So this difference in gradient technique is very useful for understanding the behavior of transistors, which is nice to know because of its huge importance. Transistors have just absolutely revolutionized our whole lifestyle, the whole planet. One of the truly great inventions of the 20th century. All right, as I was saying earlier. Okay, so all right, so we're going to find this gradient and subtract from it this gradient, and then we'll use that later. It may not be clear why we're doing this, but as usual, it turns out to be very useful. So for the moment, just concentrate on the fact, because enough details as it is. Let's calculate this gradient and subtract from it that gradient. So the difference of the two gradients. Now in this region 2, the potential is 0, right? So your your Schrödinger time-independent equation, will be of this form. We've done this quite a few times now, so you should be familiar with this. So d, now use your wave function in this region. So d squared u dx squared is just minus alpha squared. Right? We've done that before. Now, in this region 2 here, as the width gets very short, very tiny, very, very small, then the value of u here is effectively a constant. There's so little width, it doesn't vary much. So let's just call the value of your wave function in this region, region 2, which is effectively constant because there's such a small, narrow area, it won't change much. So let's just call that value of u, uw, w just for well, right? So uw is effectively just a constant, okay, uw. All right. Now we can find this difference in the gradients by if you look at it by just integrating over this region 2, we can integrate this expression. So if we integrate that expression over the regions minus a to a, which is what's going on here, well, if you integrate a second differential, and just go back to calculus, high school calculus, if you integrate a second differential, you'll get the difference of two first differentials. So instead of d squared u dx squared, you'll just get du dx. And so now you evaluate this at the limit at a, well, that's up the right hand side, okay, so RHS, right hand side, minus du dx at minus a, which is on the left hand side, right? So here we get this difference in the gradients by integrating the second differential. But this second differential, we know what it is. It's just minus alpha squared u. We have that from the STI, right? The Schrödinger time-independent equation. So instead of d squared u dx squared, we can just plug in, substitute minus alpha squared u, right? Now, so instead of this here, we can put this, minus alpha squared u. Now alpha, from definition, is just a constant. Alpha's a constant. Now it was beta that was a function of the energy, but alpha was just a constant. So the alpha squared you can bring outside, okay? So you just put this in here. So a constant, that just comes outside. Now u here, because region 2 is so narrow, u is effectively a constant, so it's just uw, this. So that's also a constant, so it can come outside. And then you're just left with a trivial integral, right? It's just, I mean, I could put a 1 here if you like. So you just got the integral from minus a to a dx. Well, that's a trivial integral. It's the answer. the result of that integral is just 2a. All right. So so the difference in the gradients, so the right-hand gradient minus the left-hand gradient, we're finding this within region 2, right? This integral here is between a and minus a. That's region 2 here, and our u here is the u within region 2, right? Within the well. Because you know, we're using this st. Now outside in regions 1 and 3, we'll do that in a minute. We won't have minus alpha squared. We'll have plus beta squared, and it'll be an exponential fall off. Okay? All right. Now a bit of a go off at a tangent slightly here. Now I'm going to need this result from the previous session. You know, if you're rusty on it, go back, previous session. So A alpha squared is equal to 2m delta. Remember, delta is your product. It's the A times the V naught. So 2m delta all over h bar squared. So I'm going to need that result in a moment. Okay, so that's a bit of a tangent. All right. So now you can rewrite this minus alpha squared uw, this constant pretty much, times 2a, and here it is here. Okay, but a alpha squared, which was I was just saying here, a alpha squared is 2m delta over h bar squared. So so substitute for a alpha squared, what I just said. Now you've got a 2 here, so this will become 4, right? So the difference in the two gradients, so the right hand side gradient minus the left hand side gradient, is equal to this. Alright? Okay, now let's calculate the difference in the two gradients by using the wave functions in regions 1 and 3. Now, the wave functions in these two regions, they decrease exponentially fast with distance. It'll be they drop off exponentially, very fast. So let's find the gradient here, this one on the right hand side, and the gradient here on the left hand side, but solving the st in regions 1 and 3, not 2. So our u, the wave function now, is the u in regions 1 and 3, and by symmetry that u will be either an even or an odd function. Alright, well, in region 1 here, x is negative, okay, so your wave function will be of this form. Now, we've done that before, so this is just revision. Now, x is negative, so this does not blow up, doesn't explode. Now, in region 3, you have something similar. So the wave function will have this form in this region, region 3, okay? And here's your st for regions 1 and 3, right? du squared dx squared equals plus beta squared u. Right? Now, let's calculate the gradient on the right-hand side here. So we're now going to calculate this gradient here. Right? It's in region 3. This gradient. Well, we know what u is. It's of this form, right? In region 3. That's u. So what's du by dx? In other words, the gradient. Right? Well, that's pretty easily calculated. It's just minus beta. This minus beta comes out times the same thing. Now this here is just u, right? That is just u. So you can rewrite this as minus beta u. Now with the same argument, this by continuity, in fact, at this point here, your u here must be equal to the u value here at that point. Now you're talking about continuity of the value, not just continuity of the gradient. No, there were four conditions. Okay, so this u here, so the u that exists in region 3 that's infinitely close on the right hand side of this barrier, that will have to be equal to the value of the u in region 2 that's infinitely close on the left hand side of the barrier. Now this width here got so small, we said effectively the value of u would be pretty well a constant, u this. Okay, therefore the value of u at this point must also be this. Okay, so we can rewrite this as minus beta uw. Okay, now a similar argument for the gradient on the left hand side. That would be the gradient here, right? Now in region 1, the wave function is of this form. Okay, now x is negative, so this falls off rapidly, decreases exponentially. Okay, so that's our function for u. So find its gradient, so du by dx on the left hand side will just be beta c, so this is just u again, so you get beta u, and the same argument, same continuity argument of the value, so u will be uw. So the left hand side gradient is beta minus uw.